Hello everyone. So in this video we are going to simulate a conjugate heat transfer problem. So I have a pipe which transports a hot liquid and I have insulation to the pipe, and as you can see there is a gap in insulation at some location of the pipe. Okay, and the whole setup stands at a place where there is a air stream parallel to the pipe at a speed of 4 meter per second. So which means there is forced convection, and the scenario is you have a shutdown and the heat influx stops for some duration of time, and as well as the flow stops, and during this period there will be a thermal cool down. Okay, what we have to do is to estimate how much does the liquid inside the pipe would cool down for this duration of time. That's the context of the problem, and we will be dealing with this 1 meter segment of the pipe and insulation. The pipe, the insulation together with the air surrounding the pipe constitutes our geometry. So for this simulation we have multiple regions, so we will deal with interfaces and we can see how to do that, as well as we will be using a directed meshing since we have the geometry as a prismatic one. Okay, so with directed meshing we need 3 basic surfaces for each of the parts. We have 6 individual parts, and for each of them we need a source surface where we create a source mesh. We have the target surface to which we sweep the surface mesh, and the third surface, which is the guide surface, which is the outer surface of each part. Okay, each of these parts apart from the water column are annular solid cylinders, and you have the outer surface and an inner surface. So the one consideration which I have made to make sure all these parts are prismatic in cross section is that the air gap in between the insulation is made as a separate part, even though it is air, and it is not combined with the outer cylindrical region of air. Okay, so by doing so we have the basic criteria for every part and can be meshed using directed meshing approach. Okay, that's one thing which I have done. So this is the geometry. Now we can set up the simulation in Star-CCM Plus. So before we start with the simulation, let us estimate the time that it would require for certain amount of temperature change analytically. For that you use basic heat transfer laws. So without the insulation, the 1 meter length of water column contains this much amount of energy, and assuming Newton's law of cooling, you can calculate the time that it would take to reach the steady state as around 1921 minutes. Okay, and with the pipe, for the pipe with insulation, you can actually calculate the overall heat transfer coefficient by taking into account of all the conductive and convective resistance. So I have considered the non-insulated length of pipe as 20 centimeter and insulated length as 0.8 meters. Okay, and using that information you calculate the time, and as I have done that, the time required to reduce the temperature from 200 degrees Celsius by 0.01% is around 1 minute. So in the CFD we will be checking this result. So initially we do a steady state simulation and find the steady state temperature for water, pipe and the insulation. So we will use those results as the initial condition for unsteady simulation, and we monitor the time that it would take for 0.01% decrease in temperature, and we will compare it with this time duration of 1 minute. It might be higher or lesser. We will check that with the simulation. One more thing we might want to use is regarding the Rayleigh number. So we have the region where water is present and the temperature of water changes gradually, okay, as it cools down. So we want to estimate whether the convection that is present is laminar or turbulent For that we use Rayleigh number. I have done the calculation, and as I am assuming from 200 degrees Celsius, if it goes to 199 degrees Celsius near the periphery of the water column, then there will be a convection present, and the Rayleigh number of the convection can be estimated as 1.3 e to the power 8, and according to that the nature of convection is laminar. Okay, we will use this condition while setting up the physics of the water in the unsteady simulation. So that's it. We can move to Star-CCM plus. So I have created a new simulation, named it as insulation gap, and we can start by importing the geometry. Okay, so we can name the body groups. So we have the air stream, we have the air gap, we have the insulation 1, insulation 2, pipe, and the water column. Okay, these are our body groups. So we have to do one more thing in the geometry part. We have to make sure we have the patches as separate for all the boundaries that we require. So we will be splitting the surface after creating a new geometry part, and we will be using a split by patch option. And in case of the pipe, currently the exterior surface of the pipe exists as a single patch, but we need it as 3 separate patches. Then only we can have a similar sharing boundary between insulation 1 and a patch of the pipe, as well as air gap and the second patch, and insulation 2 and third patch. Okay, so if the sharing phases are dissimilar, we won't be able to create an interface between them. We need multiple patches on the exterior surface of the pipe due to this reason. Okay, so we can create that here, and it can be done using the sketch imprint option. So let's hide the air gap as well as the air stream. Okay, now create 2 planes. Okay, now we can create 2 sketches on these planes, and we can do the sketch imprint option. Right click on the sketch and you can find this sketch imprint. So this is to basically split the exterior surface of the pipe into multiple patches. Okay, if we hide the insulation 1 and see, now we have 2 different patches on surface of the pipe. Okay, so if we need multiple boundaries which are shared by these patches, then we need to have multiple surfaces instead of a single patch. So we have to do a similar operation on this sketch plane. Okay, so now we have 3 different patches on the surface. Okay, so we are good to go. Now we can create a new geometry part, and once we split the surfaces, it will be better clear why we separated the patches in the first place. Okay, also while we create new geometry part, whenever you need a high quality surface mesh, always make the tessellation density very fine, as well as make sure to enable this create part contacts from coincident entities. By doing so, while creating the part itself, we can create automatically the contacts that we require. And in later stage, when we create or assign parts to regions, using the contacts we can create interfaces. So make sure to enable this as well. And also, while we did the CAD in SolidWorks, we made sure all the parts are separate and it's a multi-body part. So this is also to facilitate the creation of contacts. Okay, create a geometry scene. So you can find the surfaces by default as a single one, and we have to split it according to the requirement of different boundaries. So here we will go use split by patch. So this will be the one of the boundary which will be participating in the interface between air gap and the pipe. Okay, so we can name them accordingly: air gap, pipe. Okay, create. And this one will be a interface boundary between air gap and the airstream. So I'm naming it in such a way first letters of each of the surfaces are used. Okay, and this one will be again a boundary surface between the air gap and the lateral face of the second insulation. Okay, so I'll name it as air gap insulation to wall. Create. And we have one final surface. It will be air gap insulation 1 wall. Okay, so it's important to name it properly, otherwise it might be difficult if there is a situation where you want to create some interface manually. Now we can do the airstream split by patch. The external boundary, we can name it as environment, and this will be an interface boundary between the airstream as well as the insulation 1. So I will name it as AI1, and this one between airstream and air gap. Similarly, between airstream and insulation 2, this will be our inlet, and by default this one will be our outlet. Okay, so next we can split the surface of insulation 1, split by patch, and this is a surface shared between insulation 1 and the pipe surface. Okay, so that will be I1P. Create. This is I1A. It will be a complementary surface to AI1 which we created in the airstream surfaces. Okay, this one is I1A, and this is our I1WAG complementary to AG I1W. Create. And the other surface, so we are considering situation where heat transfer in the lateral direction is absent because of insignificant temperature gradient. So we can name it as a wall. Okay, and in boundaries we will assign it as an adiabatic wall. For insulation 2, we have I2P, we have I2A, this will be I2WAG. This is similar to W1, we can name it as W2, and this will also be considered as an adiabatic wall. So we are only concerned of the heat transfer in the radial direction, and is again convected by forced convection. Okay, so we can split the pipe surface. So here we have to check whether it is an internal or external surface. Okay, so in case of the internal surface, it will be shared with the water column, and we don't need separate patches in that interface. Okay, so we can actually combine these three patches and name it as pipe water boundary. Okay, create. And this one is PI2 complementary to I2P, and this one is PI1, and finally this is PAG complementary to AGP. And we have the lateral walls, so we can name it as W3 and W4. Yep. Next, the water column. So this again is the exterior surface of the water column, so we don't need them as separate patches, but instead it will be sharing with the PW boundary which we created for the pipe part. Okay, So we can combine these three patches and name it as water P instead of PW. And we have the lateral direction, and as we discussed, we don't assume the heat transfer to happen along the length of the water column. Okay, this is an assumption because you have almost similar temperature on the lateral faces, so a temperature gradient is nearly absent, and we can consider it as an adiabatic condition. Okay, so this can be W5. Okay, so we have named all the surfaces accordingly, and now we can create regions from parts. Assign parts to regions, create one region for each part, create a boundary for each part surface, and here you can enable create contact mode interfaces. So using the contacts we can create the interfaces. Okay, apply. So the one thing I missed to say, once we generated the parts, we can automatically, due to the condition which we enabled in the dialog box, we can automatically get the contacts. Okay, so it is also relevant to make sure that we have captured all the contacts that we require. So if we don't have the contacts, then we can't use interface generation using contacts option. Okay, so by splitting the patches and creating the proper boundaries, we can make sure that all the contacts that we require are captured. Okay, and again, if you monitor the naming, you can see if they make sense. PW and WP, they are the shared boundaries in this contact. Okay, so and all the namings indicate they are the surfaces which are involved in it. So that's one thing. Now in the regions, we can just rename this. Okay, so we have the regions and we have the interfaces created automatically from contacts. Okay, and if they are active, they will be highlighted in a yellow color. So we have between air gap and airstream. If the phase of the material is similar, it will be an internal interface, and if we have dissimilar phases, it will be a contact interface. Okay, now we haven't defined the physics, so we can do that first. So we need three physics, one for air, one for solid, and one for water. So we can do it for air first. Select models. We will be doing a three-dimensional case, and we use gas, segregated flow, constant density. So initially we are going to do steady state simulation. We are not aware of the temperatures in a steady state condition. So when you want to simulate the cooling, we have to assume a scenario where the shutdown isn't active yet. So there is a working condition. In that condition, the internal surface of the pipe will be at constant temperature, same as that of liquid. Okay, so by having such an isothermal condition, we can do a steady state simulation to find the initial temperatures for pipe, water column, as well as the insulations. Okay, and using that initial temperature condition, we can then do the unsteady simulation. Okay, so that's how we are going to do. So initially we do steady state simulation, and it will be turbulent, and for the energy we will be using segregated fluid temperature model. Okay, so that's the physics of air, and we can modify the gas properties. So I'm using properties of air at 25 degrees Celsius. Okay, now we can also modify the initial conditions. So static temperature, we can make it as 298. Turbulent intensity can be 10%. So I'm assuming values of an outdoor flow condition, and velocity is 4 meter per second. Okay, now we need physics for solids. So we have two dissimilar solid materials. One is the insulation and the other one is the pipe. So we will be using a multi-component solid model, three-dimensional. Instead of solid you can find multi-component solid, and you can use multi-part solid. Okay, and we will be using steady, and we will be using segregated solid energy for energy model. And inside the models you can select the different materials that you require. Select mixture components. So if you can find a standard material from the list, you can use that, or else you can use some random material and modify the material properties according to your requirement. So I'll use SS302 for the pipe material and some other material for insulation. I'm using a fiberglass composite insulation material. Okay, and you can modify the properties here. Okay, we have defined the materials. We can assign the materials to different regions in the next step. And for the initial conditions, we can specify the initial temperature as 298, but we can modify them later, different regions specifically. But these are the continuum values which will be used in a default situation. Okay, so we can create the physics for water as well. Three-dimensional liquid segregated flow, steady, and we used the Rayleigh number calculation to find the nature of the convection, and we are using laminar. Within the water column, the temperature variation will be gradual, and we don't have such a high turbulent forces active, so we can use laminar condition. Okay, and for energy we'll use segregated fluid temperature. Okay, and models you can check the properties, modify if required. Okay, so now we have the physics. Now we can assign physics to different regions. So here, so air gap is air stream is also air. Insulation 1, we can change it to solids. Insulation 2 to solids, and pipe also solids. Water, physics water. Okay, so as we change the physics, we can find here the interfaces getting updated. So this is an air-to-air internal interface as we mentioned, and this one here is between air gap and insulation 1, and it's a contact interface since we have a solid and fluid involved in the interface. Okay, and we have a solid to solid internal interface between insulation and pipe, and we have pipe to water contact interface. Okay, next we can define the boundary conditions. There will be adiabatic walls, there will be interfaces, and we need inlet and outlet conditions. Okay, for air gap, all the phases are involved in interfaces. And one thing to mention is that if you see the boundaries, you can find the surface or boundaries which are involved in the interfaces to appear as wall conditions, and we don't have to worry about those, because when we initialize the simulation or initialize the interfaces, these walls become a dummy object and it won't be active in the simulation. Okay, and the interfaces will be the active boundaries. Then for airstream, we have the inlet, which is a velocity inlet, static temperature we can mention 298. (4 meters per second). Okay, and outlet we can change it to a pressure outlet. Just modify the temperature. And again, as we discussed about the walls, we assume the heat which is transferred across the insulation surface is convected by the forced convection through the air, and we assume that in the radial direction across this environment boundary there isn't a significant heat transfer. Okay, again we consider here this surface as wall but with slip condition as well as adiabatic thermal condition. Okay, shear stress specification is made to slip, and the other phases are part of the interfaces. To the insulation 1 we have interfaces as well as a adiabatic wall. So the walls by default will be adiabatic, so we don't have to modify them. And inside physical values you can specify the material. Okay, you can find the materials which you have added. Just right click on one of them, which is the material, and you can in parts select the component, and do this for insulation 2 as well. And for pipe, select the stainless steel material. Okay, so we have the materials given, and for water we have the interface and we have the two lateral faces which are again adiabatic walls. We have the regions specified, we have the boundary conditions specified. So now, as we mentioned, we are going to do a steady state simulation first. So we need to specify an isothermal temperature condition to the water pipe interface. Okay, so here check the physics conditions. You can find thermal specification, and for the interface by default it will be conjugate heat transfer. So initially to do the steady state simulation, change it to a specified temperature condition. Okay, and you can modify the temperature here, and I will keep the temperature of the liquid, which is 473 Kelvin. Now we have the conditions. Next we need to create the mesh. For that we will be using a directed mesh. So new mesh, and you can find directed mesh here and select the parts. Okay, and if you right click and edit the directed mesh, a new window dedicated for directed meshing will appear. Now, as we discussed, we need source faces and we need target faces, and all the lateral faces will be the guide surfaces. Okay, you can right click and see add to source option here, and once you do so, the surfaces will be highlighted in green. Okay, all the source surfaces will be highlighted in green. So we can primarily select the main source and targets first. Okay, and the other face will be target. Okay, we have more sources and targets present inside. Since we have the air gap part present inside, the geometry is similar to a stacked geometry, and you can find how to do directed meshing for stacked geometry in the documentation as well. Okay, if I make it transparent, and you can basically select the sources from tree as well. So click here and you can find. So the logic is the mesh for each part should start from the source and end with the target. Okay, and if you are specifying the source as this direction, then you follow the trend for the air gap part as well. Okay, so if we start from here, the insulation 2, the source for the insulation 2 is specified, Now the target for insulation 2 will be the other end of the insulation 2 component, and for the air gap the source will be the left face, or the face shared with the insulation 2. So that will be this one, air gap insulation 2 wall. Okay, and for the insulation 1, or the face will be in insulation 1, and it will be the wall shared between air gap. Okay, so these are the two sources present in between the geometry, so they are highlighted now. And if you select the target surface and go to the tree, we can do similarly. So for the insulation 2, the target will be the insulation 2 wall, and for air gap the target will be air gap insulation 1 wall. Okay, so we have them highlighted. So this is how you select the source and targets. It's you just follow the source target pattern. Okay, now we have the sources and targets. Next we need to create a source mesh. So new source mesh, automated source mesh, select the part. I will use polygonal measure and prism layer measure. Okay, you can modify the controls. So I'll use base size of 1 centimeter, and I will keep the growth rates slow. Number of prism layers 5, layers touching 20%. Prism layer total thickness I will keep 2 mm. Okay, also you can add local controls. I need to specify the surfaces where I don't need prism layers, so I am using a surface control for that. So I'll just name it to okay. And in the controls, if you can find it here, disable, and you can select the part surfaces where you don't require them. So I need prism layers at the interfaces, but I don't need at other walls. Okay, so I don't need them here, and I can have it here. And for the airstream, I don't need it on the outer surface, or inlet outlet, and you can keep for a I am using it for the interface, but basically you can keep prism layers only at the fluid side of the interface. I think that should also work. And for insulation 1, I don't need it here and at the walls. Okay, for insulation 2, I need it here and the walls. And for the pipe, I don't need it here and here. And for water as well, I don't need it on the lateral faces. Okay, so I have specified all the surfaces where I don't need prism layers. Okay, we can now create the source mesh, update. Okay, and you have the source mesh created. Now we need to sweep the source mesh to the target face. For that we have to create a volumetric distribution. Okay, and here you can adjust the sweep properties. So I'm giving 10 number of layers, and stretching function, maybe you can create the sweep such a way that you have high density mesh on the edges or the source and target faces, and a bit more less dense mesh in the middle, or you can maintain a constant sweep condition. So I'm using constant for the time being, and you have different other options. Okay, so next I will generate the volume mesh, swept volume mesh. Okay, so this is our directed mesh. Okay, you can find it well arranged. Okay, and our prism layer controls basically considers no prism layers or on the surfaces that we specified. Okay, and I have kept the prism layers at the interfaces, and maybe you can see the internal geometry as well. So you can close this and create a mesh scene. Yes, and you can close directed mesh. Maybe you can save, and in mesh scene hide some parts, air gap, airstream, insulation 1, insulation 2. Okay, so this is how it looks inside, and you have the prism layers where you required. Okay, so we have the mesh and we have all the conditions required for the simulation. Now we can add some post-processing scenes and reports, and we can run the simulation. We need a temperature scene. So before that, we can create a section plane. Yep. Okay, now we have the temperature scene. Next, we can have some reports. So we need to monitor the temperature of insulation and pipe, and we want to find the steady state values, as well as we can use it to monitor convergence. So I'm using volume average of the temperature, pipe temperature, parts, regions, pipe. Okay, and you can duplicate for insulation 1 and 2 and change the parts here. This is insulation 1, this is insulation 2. Okay, so now we have the reports. You can create monitor plot. Okay, so we have everything set up for the steady state simulation. Now we can initialize and run. Okay, so now the residuals are low and we have convergence. Okay, now let's stop the simulation and just record the temperatures. So next step is the unsteady simulation. So we can modify the boundary conditions or the initial conditions. And the first thing, we have to reassign the thermal specification at the pipe water interface back to conjugate heat transfer. Okay, then we have to give the initial conditions. So for water, initial condition is 473 Kelvin. Okay, and for solids we can use region specific values. For that, here you can find physics conditions, initial condition option, and use region values, and this will pop up. Here inside static temperature you can give, so this one is insulation 1. For insulation 1 we found 370.768, so we can give that value. And for insulation 2, it's 371.581, and for the pipe it's 472.92. okay, so we modified the initial conditions. Next we want to change the solvers from steady to unsteady. Deselect steady and use implicit unsteady. Okay, so we will be checking the analytical result, that how much temperature drop would happen in 1 minute time, or to reach 0.01 percentage drop, how much time it would take. So we will monitor that result. We can choose our time step and stopping criteria according to that. Okay, I will use a 5 millisecond time step. Okay, and stopping criteria I will use inner iterations 15. Maximum physical time as 70 seconds perhaps. Okay, maximum steps around 15,000. Okay, so now we have specified the stopping criteria and changed everything to unsteady. Maybe we can add one more report, which is to monitor the temperature of the water column. So copy, paste, parts, regions, water. Okay, we can create a plot for that as well. Yes, so now we have everything. We can initialize and run the unsteady simulation. Before that, clear solution. So everything, all the plots should be going down since it's cooling, and it's starting to become a plateau, and then it would drop down, and this rise should be because of the errors in the initial condition approximation. Okay, so we can wait for convergence and see the results later. So the simulation ran for 70 seconds and the residuals are converged. It's really low, and relative to the continuity and momentum residuals, usually energy residuals converge slower. So but it has gone to the order of -5. It's fine, and this is the temperature seen at 70 seconds, and everything should be cooling. So this is the pipe temperature plot, and it has dropped down to 471.6 Kelvin, and for insulation it's at 372.36, and this is for insulation 1, and this is the average water temperature plot. So by 70 seconds or by 1 minute it's like 472.94, and what we discussed was 0.01 percentage drop, and that corresponds to around 472.9527, and that's around here. And as you can see, the time it took is around 54 seconds, so that's like 5 seconds short of 1 minute. So that is a good correspondence with the analytical calculation that we did. Okay, so that's the results. So the simulation seems to be correct enough with the analytical calculation, and hope it's helpful for you. You can try it out, and thanks for watching.